Hi everyone, welcome. Welcome to another spring showcase. And thank you for joining us today, along with Severn Trent Water and the fantastic supply chain that has supported them with the trials and implementation of leading digital twin technology to optimise their wastewater sites. For those who aren't familiar with Spring, we are the Centre of Excellence for Innovation in the UK and Ireland for innovation. And our main objective is to enable the effective delivery of innovation and collaboration by creating centralised intelligence for both water companies and suppliers. Our mission is to attract, connect and support innovators across the industry to accelerate transformation. And that's why we facilitate and host knowledge transfer events such as today. Through the knowledge sharing service offering, Spring supports the transfer of learnings from an innovation project to the wider sector, creating project legacy that helps innovators to identify and adopt the right solutions at a greater pace. So last year we actually partnered with Ofwat, the economic regulator for England and Wales, to build out a view of what best practice knowledge sharing actually looks like. We brought together senior leaders and innovation managers to design a vision for knowledge sharing and what actually is it that we're trying to achieve through knowledge sharing. So ultimately, the answer was that we want to unlock faster adoption by creating a world-class knowledge sharing culture. And the 6 principles we created to support with this are here. So number 1, learn from what already exists before committing to innovation projects. So to aid this, we created the Spring platform, which will be linked in the chat in a moment. And that hosts a multitude of project case studies aligned to the priorities laid out in the Water Innovation Strategy 2050. Again, that will be linked in the chat in a moment for anybody who wants to take a look. So links, these go alongside the showcase recordings too. So anybody who wants to watch today back, you can do so on the Spring platform and it'll be alongside a written case study as well. So number 2 is target innovation insights to the right audience to meet our objectives. So we want to make sure that we've actually got the right people here listening to these lessons that are being shared. So for today are the relevant people on this call who can actually take action on the knowledge shared today within their own organisations. Number 3 is insights are regularly shared through multiple channels from day 1 of the project. So historically, knowledge share does happen at the end of a project, and we really want to start moving the sector towards a model where we're all sharing from day 1 of a project, making sure nothing is missed along the way. Number 4 is all about centralising and opening up that sector intelligence. So we want to make sure that we're all being open and honest when it comes to the knowledge from innovation projects. And we want to make sure it's all in one place, i.e. Spring, because fragmented knowledge is much more difficult to engage with and learn from. So back to today, I'm just going to give a warm welcome to all of the audience members joining us live, who are joined also by the UK and Ireland water sector, including water companies, supply chain, academia, and lots of overseas colleagues too. So welcome to the call and thank you for joining us today. As always, we'll be introducing a poll during the event in order to gain your feedback. Your voice really matters to us, and providing feedback and answering our poll questions is one of the most impactful ways you can help improve future Spring events. Your insights not only help us to understand what worked well and what could go better, but they also ensure that each experience is more tailored, engaging and valuable for everybody involved. So we are testing out a recently new poll function. So please do submit your answers when you see that come through and let us know if it hasn't worked for you for whatever reason, just so we can monitor that that's actually working for everybody. Perfect. So just to run through the agenda really quickly and introduce our speakers before I hand over to Jess to kick off. So we'll be starting with an introduction to speakers, of course, and then we'll go into context and overview. An overview of the Strongford site and the requirements for that particular site, model types and allocation, GPROMs and mechanistic models, data models and optimisation, model integration and demo. We'll see some benefits so far, and then we'll go into a quick break, followed by some key lessons in some more detail, and then finishing up with our usual Q&A. So do keep making sure to put your questions in the chat as we go through today. I'll next hand over to Jessica Alse, Strategic Innovation Business Lead at Severn Trent, who alongside James will be delivering that introduction, who is the Control and Automation Architect at Severn Trent. We'll then hand over to Di, who is Senior Innovation Technical Expert at Severn Trent. And then we'll hear from Jeremy Black, Chief Engineer at AtkinsRéalis, Adam Cartwright, Industry Strategy Director for Waste and Wastewater Companies at Siemens, Timon Di, who is Project Manager at Xylem, and Jeevan Samuel, who is AI Solutions Director at Sand Technologies. So a really exciting lineup for you today. And with that being said, I'll now hand over to you, Jessica, and James to kick us off. You might just need to pop your cameras and mics back on if you're speaking.
Can you hear me? There we go.
Yes, we can, yeah.
So just a quick introduction. So my name is Jess Al. So I'm responsible for any innovation we do with a strategic lens, that covers physical, biological, the Net Zero Hub, and any of our digital and data innovation. So right now I'm going to take you a little bit on the carbon journey we've been on, just to give you a bit of a context of why we're doing the digital twin. So started for 10, just a little bit around Severn Trent. So some of you on the call might know a bit about us, but just to give you a bit of an insight to us. So we are a Midlands based FTSE 100 company. We have just around a million people across our region providing waste and water services. We're around 10,000 people employed and around 2,800 direct suppliers. We maintain just under 50,000 kilometres of clean water and just under 100,000 of sewer pipes. We've recently been awarded the top 4-star rating from the Environment Agency as part of our EPA, and this is the 5th year running that we've been able to get that star rating. We've also recently been awarded outstanding status as part of our final determination from Ofwat. And we've recently signed, well, not so recently anymore, but we signed what we call our carbon triple pledge, which I'll go into a little bit more in a couple of slides, which is all about being net zero by 2030. We've also signed up to the science-based target initiatives, because that's all aligned to our strategy, which is all about being sustainability-led and performance-driven. So just a bit into our journey into net zero. So just a little bit of background and context. So back in 2019, which feels like an age ago now, we signed what we call our triple carbon pledge, and that's all about being net zero by 2030, with 100% of our energy from renewable sources, and we're around 66% of that at the moment. 100% of our electric fleet, our fleet is electric where available. So we've started with our vans for our operational colleagues, and we're actively looking into our large vehicles at the moment. We've also signed up to science-based targets, so we have a big emphasis on scope 1, scope 2, but we're doing a lot of work in our scope 3 emissions. And for those who don't know that, I will explain that in the next slide. And just to give you a bit of insight to how we've been able to progress on this journey, sustainability is at the heart of our business, and one of the things that we've been able to do in the last AMP is we generated income for innovation through a self-imposed carbon tax. So what we've done was impose any business unit that has process emissions with tax to then fund that money back into innovation, and that really drove our emissions monitoring, our optimisation trials, and the money that we funded a lot of our Ofwat innovation funds through. In terms of where do emissions come from, so just a bit of insight into that. So across wastewater treatment works, we have 3 types of emissions. So first of all, it's carbon dioxide, and that is heat needed for some of our treatment processes. This is specifically our anaerobic digestion plants, or our thermal hydrolysis plants need natural gas to be able to keep to the temperatures. We also have nitrous oxide, which is 273 times more potent than carbon dioxide, and that is emitted from our biological treatment processes. We have fugitive biomethane, so that anaerobic digestion plants that we have that produce biogas, which is a valuable resource, sometimes leak methane into the atmosphere. In terms of scope 2, when we run our processes, we need to use that electricity. So we do aim to produce that ourselves, or we buy REGO backed electricity, which it means it's renewable energies of obligation. In terms of scope 3, so this is chemicals that we have to remove nutrients that can't go into the water course, such as phosphorus, and any embedded carbon, such as the concrete that we have to build our assets. And in the offset world, we do export any excess electricity or biogas to the grid. This then displaces fossil fuel-based gas and gives us what we call an offset. To give you some pictures of where we actually see these emissions on the site. So our nitrous oxide byproduct is produced during nitrification or denitrification of wastewater treatment. This is emitted from activated sludge plants, trickling filters and nitrifying filters that we have on most of our big, larger wastewater treatment works. Methane is produced from our anaerobic digestion, and it's emitted from uncovered sludge holding tanks, cake pads, or incomplete combustion, such as flaring boilers or combined heat power engines. As I mentioned earlier, carbon dioxide is mainly used for energy on site. So what is the approach that Severn Trent has taken to combat our carbon emissions? So the first thing we did is all about understanding our emissions. We really invested heavily on a monitoring program to monitor 40% of all of our flow into our works. And from this, we started to understand that the emissions from our works are more than what the carbon accounting workbook that's used for the water industry reports at. So to give you an example, we are having data that's around 4 times what the standard non-emission factors are used in the carbon accounting workbook. And we have taken a priority to understand our baseline so that we can understand how we can reduce, remove, or replace and optimize to reduce those emissions. The second thing we've done is make sure that we use a hierarchy of management priorities. So all about understanding how you remove that carbon. So you should always reduce, replace, remove, and offset that. So in terms of our larger net zero target and our net zero hub, all the solutions that we have been able to implement are following this hierarchy. And finally, we've been developing the industry blueprint known as our net zero hub at Strongford in the Stoke-on-Trent area. We've implemented a collection of technologies with the partners on this call. And by delivering the commitments of this, we'll be able to share learnings wider. And our first sharing today is of the digital twin, and that's also been fundamental to our AMPE UMI. So these are our modelled expenditure business cases. Ofwat awarded around 500 million across 33 streams to deliver net zero, and of these 59% of that funding has come to Severn Trent through the technologies at the net zero hub and including the digital twin. So just to quickly touch on the net zero hub. So we've done a lot of work in carbon, we've done a lot of different trials, but the one thing that we really wanted to understand is how does that work in real life? How do you retrofit these technologies into aging assets, into live plants? And the concept was to implement this at Strongford as a single flow sheet. This combines different types of technologies. We've got physical, biological, chemical, but we've also got the digital technologies, which is the digital twin. So we're not going to be talking about the other technologies today. We're going to focus in on the digital twin. I'm now going to hand over to James to take you through what that means.
Brill, thanks, Jess. Yep, hi everyone, James Ballard, Severn Trent as well as Jess. So strategic architect, and my background and focus is on control and automation. So I'm here to open up the question that's on everyone's mind. What exactly is a digital twin and how does it fit into this story? And of course, what I'm going to cut to the chase for you guys, because everybody's got a view and everybody's got a different answer for digital twins. So I'm going to be clear about what it means for us and set the scene, I guess, for the rest of the presentation. It's going to take you on our journey. So as a strategic architect, I need to take a step back and take a holistic view across the world that we're trying to build. This is source to tap and drain to river. We're going to, we are building a world where we're delivering really high quality drinking water and safely taking waste away. So specifically think about the waste. You've got things like spills, floodings, pollutions, greenhouse gas emissions, energy, chemical. So across all of this source to tap, drain to river, we've got tens of thousands, possibly even hundreds of thousands of assets, pumps, valves. We've got treatment processes, we've got biological processes, we've got chemical processes. So what we need to do is build a world where all of this is joined up and optimized. So that's ultimately a world where we need to get to. So how does the digital twin fit in for us? We need to be building a tool that can interconnect, join, take data, simulate it, and create an optimization support that can help us really deliver. Because if you think about just how many variables there are, you've got the variables in all of your assets, your processes, environmental factors, weather. So there's a lot of variables, and we need some support. So inspiration for digital twins. As I said before, it means different things to different people. We know we need to create this tool that can help us to optimize the end-to-end journey. What we don't know, and certainly what we didn't know when we started this project, is to what extent do these things help us? So 3D models, data-driven models, mechanistic models, user interfaces, how smart do they need to be? How much analytics do we need? And really also, where do we get the benefits? So actually, how much benefits can be released in a short amount of time through visualization, maybe user interface, versus how much benefits do we get through some really deep analytics and modeling? And then the big question for all of these things, I'm sure they all have a part, and you'll hear about this as we go on, is how do we bring them all together? So how can we build a digital twin that's scalable, sustainable, manageable, when it needs all of these different components and we need to join them all together? So to be really clear for us, we needed some capabilities. We needed to know what our twin needed to deliver in order to know that we've actually made a successful tool and that it's doing what we need it to do in order to help us deliver that end-to-end optimization. So those three things: visualization, simulation, and optimization. There's going to be an amount of benefit released when we can actually visualize what's going on right now. And that could be from sensor data all the way through to contextualized KPI information. So how am I performing today compared to yesterday? Just seeing that information contextualized for you can help you make better decisions. To go one step further, we need to be able to predict the future. So given external factors like weather, what's going to happen tomorrow? How can we help to prepare? Again, think about all those variables that we talked about earlier, the trade-offs. What if I turn this up a bit? Something else might fall down. So I really need help. There's too much going on. Let's simulate it. Let's see how it's going to go. And then we can make some more informed decisions. And finally, optimization. Well, that is a real goal, isn't it? So how can we get to a place where the digital twin recommends settings, recommends set points, and actually tells us, based on the conditions, based on what we're going to see tomorrow, if you tweak things in a certain way, you're going to get the benefits that you want to see. So these are the three things we were aiming for. Key considerations before I open up to the rest of the journey. We've got data. I'm going to talk a lot later on about, I'm sure everyone will, about availability, quality, and usability of data. So we definitely needed to consider what data do we need and how do we process it, the format, the type, the availability, everything there is to know about data. Models, how many of them, which ones, in which order, and then the big question mark is people and processes. So we think a lot about the technology and the fact that we need a model and we need some data, but actually, who's looking at it? Who's maintaining it? Who's responding to it? How do we want them to respond to it? All of this needs to be solved and answered on our journey to creating this tool and this optimization support. And finally, just building on what Jess said earlier, off the back of this project, which has been incredibly successful, we are going to be taking this through AMP8 into scaling what we've done across 33 sites, specifically targeting greenhouse gas emissions. So although I take a step back and look at the holistic end-to-end journey, this is our starting point. We need this to prove and deliver and demonstrate the power of optimization support. As we scale out and as we build out through AMP8 and AMP9, we'll be looking to integrate and build on our digital twin capability across the end-to-end. But what we'll be talking to you today will be specifically targeting on greenhouse gas emissions. And with that, I will hand over to Di to talk us through the beginning of Strongford.
Thank you so much, James. So my name is Di. I'm a senior tech expert in the innovation team at Severn Trent. I have a background in the treatment process, and I'm currently working on both the physical and digital aspect of the Strongford project. I'm going to give you more detail about the Strongford and also our expectation of the Strongford digital twin. So Strongford is actually located at south of Severn Trent area and receives the wastewater from the surrounding places. The site serves a population equivalent of approximately 400,000 people, and is around the fourth or fifth biggest within Severn Trent. It functions not only as a wastewater treatment work, but also district sludge treatment center, receiving sludge from our satellite site. From a process perspective, Strongford follows a typical treatment flowchart. On the water side, the treatment process includes preliminary treatment through screening and degritting, primary treatment via mechanical settlement, secondary treatment mainly using nitrifying activated sludge process. On the sludge side, both indigenous sludge and also the import sludge will undergo following steps like thickening and dewatering first, and then thermohydrolysis, which enhances the sludge digestibility and also provides pasteurization, and then anaerobic digestion producing biomethane, and also the post-digestion dewatering, resulting in biosolid suitable for agricultural use. And finally, the sludge return liquor, which is something that we produce. The really strong wastewater we produce in the sludge treatment is treated using a high rate activated sludge process before it is returning back to the hand of the work. So to just like recap a little bit what Jess had previously said, the site actually has like 3 key process emissions. The nitrous oxide generated during the biological nitrification process, such as activated sludge on site here. And also it actually comes from the wastewater and also the treatment side, because we both have used activated sludge to treat our wastewater. And the methane emission sort of like slipped from our sludge treatment process, and also the carbon dioxide produced if we need to use natural gas on site to generate heat and electricity to meet the site's energy demand. Some is for the aeration or pumping for the treating the wastewater, and also the heat for warming up our digester, and also mainly for the THP process. Our expectation for the digital twin is obviously to leverage advanced models to inform better operational control, and so to reduce those like 3 key types of emission I just mentioned. And therefore, the digital twin must be capable of visualizing, simulating, and also most importantly, optimizing the process emission. And equally important is the quality of the final effluent, which has a direct impact on the environment. So as such, the same requirement, visualization, simulation, also optimization, also applies to the final effluent quality. And ultimately, our goal is to minimize process emission while ensuring consistently high effluent quality. And so now I'm just going to pass on to Jeremy to talk about the model type and allocation.
Thanks, Di. So I'm Jeremy Black. I'm Chief Process Engineer at AtkinsRéalis. I'm going to pick up from Di on we established what we want the digital twin to do as a long list of requirements. And then how do we take that forward into deciding, well, how are we going to achieve this? How are we going to produce models? How are we going to collect the right data for them? And then I'll hand over to the other partners we've been working with to talk through how they've contributed towards that. Just to start with, very simply, the main point to start with is to establish what's the appropriate level of detail we want to go to. And there's a trade-off. So a simple example would be, I could just predict the greenhouse gas emissions, OPEX, final effluent quality with a model that only relies on measuring the flow to full treatment coming into the works, nothing else. And I can predict all the things I want to do. If it then tells me I've got a problem or something, it's not going to give me any more information about where or when to look on site. So very easy to do, very quick, but not particularly helpful, especially when it comes to doing anything. At the other extreme, we could go for a model that goes down to every single light switch on the site, and it would tell me exactly where to look every time there's an issue, a potential for optimization, and so on. That would be incredibly difficult to do and very expensive. So it's trying to find the sweet spot, if you will, at the appropriate level of detail, and that requires a very good understanding of the whole process. From end to end, as James has described it earlier. So seeing it as a holistic system and understanding what's significant as well. And as Jess has already alluded to at the start, and then Di and James have built on, we are looking at activated sludge plants as one particular area of focus, and the other will be the site energy arrangements in terms of electricity and natural gas and biogas use. So that then leads us to, well, what sort of models am I going to be using, and there's a number of different types available. I'm just going to quickly run through these. And so if we just go from left to right on the top row, empirical models are just very simple, almost rules of thumb. So for example, a sludge thickener, a raw sludge thickener, a SAS belt or something. I'm just interested, I don't want to go into belt speeds and wash water rates and everything. I just want to know what's the percentage solids capture. And I just use a simple relationship. It's 95%. I'm just going to assume that. I could do it in a lot more detail, but that's what we think might be appropriate for this digital twin. Then we might go for, on the second row, a simple mechanistic model, which, for example, a CHP engine, we could have just said a simple thermal efficiency or electrical efficiency, but we want something a bit better than that. So we want to use the performance curve for the CHP engine, but it's still a relatively simple model, a single input, single output. Then there's complex mechanistic models, and that's where you've got multiple variables, inputs, multiple relationships going on. And most of you, or many of you, will be familiar with activated sludge models, and maybe anaerobic digester models, and that's where we want to look more at using complex mechanistic models where they're relevant. And in particular, this will be the activated sludge process and the nitrous oxide emissions. And the other type of model that we want to use in this digital twin is quite different. It's a data model, which is, it treats each process stage, if you will, as a black box. We're not trying to understand how it works. We're just understanding what it does. And you're looking for correlations from observed data. And we've used those within the digital twin on the influent flow, linking that with weather forecasts. And as Xylem will talk about, for nitrous oxide modeling as well. Right, so different types of models, and then we've got different areas of expertise amongst the partners here. So very quickly introduce those. So Severn Trent are the sort of the host organisation, the client, and then within that, Santec are providing a lot of the wireframes, which they'll explain what the digital twin will look like, what the user experience will be, knitting together the various models. Ourselves as AtkinsRéalis provide the project management, the understanding of the carbon accounting, working especially with Severn Trent and Di in particular, how this process works, what's significant within the process, where we need to go into more detail. Then Siemens will follow on from this, talk about their ASM model, their GPROMS model, and Xylem will talk about their data model. So we've got these different organisations, each bringing areas of expertise to it. That's meant deciding as a team, as a group, how do we allocate these models? So the inlet works, and the floater works based on weather forecasting, that's being done by Santec. Siemens, who we'll talk next, will do the bulk of the effluent treatment, which is primary treatment and secondary treatment. Within that, Xylem are doing a data model for the activated sludge plants, which they will talk about, to look in particular at nitrous oxide emissions, that being a critical consideration for the whole net zero project. And the sludge stream is again managed by Santec, who also will then are knitting all these different models together. So that's a quick overview. Just to put that within the end-to-end workflow process, we started off with the requirements from what we call our users, and we allocate model types. That enables us to say, well, what data do we need? How are we going to collect it? And data cleansing, building the models and validating them. And finally, where we're up to now really is the testing, and then the user training, and then how are we going to maintain the models. So that's the overview of the overall process. Now I'm going to hand over to Adam from Siemens to introduce the work they've been doing with GPROMS.
Brilliant. Thank you, Jeremy. And a pleasure to speak to you all. What an exciting project this has been. I think, as Jeremy introduced there, mechanistic modeling is where we're understanding taking the fundamental understanding we have of the physics, the biology, and the chemistry, the equations that describe those processes, and then bring those into the model for the actual plant itself. And importantly, this is not new for the water and wastewater industry. It's also not new elsewhere. Many of us will be familiar with using BioWind, Sumo, GPSX, West. There's a number of products that are already used for the design of plants using mechanistic models. What's different in what we're talking about here is the real-time implementation of that type of complex mechanistic model in the operational environment, so not just the design environment. And because there's a lot of equations brought together, a lot of information and data, the challenge is how do you run that in an operationally useful time frame? And the good news here is what we're doing as Siemens, and I think this is always essential in innovation, is looking outside and seeing what we can bring into our sector to be able to say, okay, this is how we can benefit from investment that others have made. So in this case, it's using mechanistic modeling platforms that are used for real-time optimization in other industries and bringing it to water and wastewater. And importantly for us, that means taking those proven, tried and tested and publicly available models, such as activated sludge, and bring them into that environment. So we have a trusted mechanistic description of the process. Actually, so what we're talking about here when you say GPROMs, that's just a Siemens product name. It doesn't matter. The key point here is actually we're just talking about using the mechanistic description we know and understand and using that in a real-time environment. So practically, what does that mean we're able to do? If we just start off here on the left-hand side with bottom left with monitoring, one of the things that is actually a foundation for all models, whether data-driven or mechanistic, is being able to ground truth the output of the model with what's actually being monitored on site. And one of the benefits of being able to have a model that you validated running is actually you can easily identify when you have data points on site that are outside of their normal trend. At that point, you can then evaluate and see, is it a problem with the model, or actually, as is often the case, is that a sensor that is no longer working, drifting out of calibration, or a problem? So it helps you to be able to monitor the site. The next level beyond that is actually to be able to deploy soft sensors. So this is where you don't have a physical measurement in the site, but instead you have a derived insight which comes from the model. So, for example, biological oxygen demand, often that is something that is very difficult and not commonly monitored throughout the process. And that is something that you now have a soft sensor for that within the model itself. And you can see a range of other different parameters there as well. So if you have a model that you've validated and tested, suddenly you gain greater insight into the different parts of the process. What I'm going to be showing here is about the simulation and optimization capabilities. It's going to look very much like something only a process engineer would want to trust. So if you're not from a process engineering background, don't worry, you'd probably never engage in this level of detail. What Jeevan will show later is the visualization end, which is what operators and users would interface with. But importantly, another key feature that is brought in here to enable the simulation capability is forecasting. And then finally, as Jeremy alluded to earlier, one of the differentiators of GPROMs is in effect all those equations that are present are solved simultaneously to be able to then give you the results of that specific scenario that you've run, and that then allows you to run through all the different scenarios you need to create the optimization, because the optimization is a result of testing a wide range of different parameters. So in this case, you'll have a sense of the scale of it as the video in the next slide shows the flow sheet. But what we're talking about here is a very large number of potential data points linked together with a very large number of equations, which all includes the activated sludge models 1, 2D, and 3. So let me see here. Someone can tell me if the video doesn't work. Hopefully that's working. So what you can see here now is the actual model of the Strongford site. As Jeremy showed earlier, you have primary settlement, the activated sludge lanes, and then final settlement. On the left-hand side of the video, you can see there's an existing flowsheet library from which you can then drag and drop components on, and then you can copy and paste and replicate those components. As the video is showing as it goes through at great speed there, actually for each of these parts of any given process area, you actually can then configure and set the different parameters for each of those unit operations. And as you do that, you can actually choose options that are of greater detail or less detail, depending on how much information you have about that. And this is where often the information that's been useful at the design phase is very, very helpful if you've got that. And if you don't have much information, you just use the detail that you have and make some assumptions. Importantly, these models here interface with the AI-based models. And this is one of those things that Jeremy showed on his very high-level architecture and will be expanded in more detail later. So what's really important here, the takeaway for this, is you have a highly detailed, as Jeremy called it, complex mechanistic model that then interfaces with the AI models. And these then allow you to run the simulations and the optimization. So let's look at the next slide, where we'll see here an example of the simulation in operation. So in this case here, you can see within the flow sheet itself, you can then embed the inputs and you see the outputs of the simulation for what comes in. You can set the different constraints. And importantly here, what we're talking about is going to be defining energy-based criteria. So all those different inputs, the chemicals, the ferric dosing is included in here. And then importantly, we've added the nitrous oxide modeling, which I'll expand on in a moment. So once you then set the constraints and the limits of the scenario that you want to run, you then run that and you'll get the output from the model. And the output from the model is then what will be pulled through in the visualization, which Jeevan will show you later. And importantly, because you're looking at about both the chemical inputs, you're looking at energy, while the focus here is on net zero and nitrous oxide, this allows you to do that within the context of the overall performance of the plant, to ensure that you do that with an eye on OPEX and understanding the energy implications, but also that you do that within a way that allows you to understand the final effluent constraints which you have from your consent, and to ensure you operate with an appropriate level of risk margin to ensure you always meet those constraints. One of the things that we've often found is that the power of these types of models is it allows operators to better manage that risk margin, which in itself is a great driver of efficiency. Just to close off with a point here on the nitrous oxide sensor, this is where mechanistic modeling, AI and mechanistic modeling both have their pros and cons. And a point that we'd make here is the physical mechanisms around nitrous oxide generation are poorly understood. There are 4-step models, 5-step models, 3-step models, multiple different ways. And actually, there are many things that we do understand, but many things we don't understand. So what's really important here is that the model here reflects the validated data from the site. So you have something that works and is reflective for this site. And this is one of those things that as a sector, we need to be better at confidently monitoring elsewhere. This is then allowing you to potentially have that nitrous oxide soft sensor. So in this particular case, the result of the optimization, when you run that, is you'd have and this is the results that we're in the process of validating, an up to 30% reduction in nitrous oxide while keeping your final effluent constraints. But in order to do that, you then need to increase the energy by about 1%. So the result of those recommended set points, actually, we think can lead to some of those benefits. And that's what we're going to be in the process of validating. So I'm going to hand over from there. That's the output of the complex mechanistic modeling of the secondary stage. And I'll now hand over to Timon.
Great, thank you very much, Adam. Okay, so today I'll walk you through Xylem's approach in terms of building data models and enabling optimization within the context of the digital twin for Strongford. So our optimization approach fundamentally relies on a 3-step methodology of sense, predict, and act in order to achieve optimization. So we map and identify correlations between data and variables. in order to make accurate future predictions and based on those predictions, provide real-time recommendations that feed into a digital twin, which acts as a decision support system for operators. This approach has been implemented on 40 plus projects worldwide and really enables a multi-objective optimization, so improving effluent quality standards, minimizing energy and chemical use, but also anticipating on variable influent loads, stabilizing the processes as a result, and really controlling the processes as well. So just to touch on our solution and the implementation of that. So the solution, I'll click through briefly, really relies on 7 steps. So starting from a site audit, data analysis and review, which takes a big portion of the implementation phase. We build initial data models and design an optimization strategy before integrating the solution within the existing business processes to then validate the performance of those models and also train the operators on that. But the key point is that for every step along the way, we combine Xylem's expertise, be that on data science or specific water treatment expertise, with the local operator knowledge, and we rely on their support throughout each step of the implementation. So the end result really is that through a joint effort, we don't build a complex black box model, but a well understood technology that supports improved decision making. I saw a comment go by that the slides aren't moving. Is that correct?
I think you just need to take control. Time and I still have control, so I've moved it on for you.
Ah, there we go. Okay, is that back?
Is that the right
Is that
slide?
up to date?
We're on solution implementation slide.
Yeah. Okay. Yeah.
Perfect.
So indeed, so those were the 7 steps that we go through. And again, I think the key point here is that along each step along the way, we combine our own expertise with the local site knowledge in order to build a solution which is very well understood and is not a complex AI model that where the inputs or the outputs aren't quite understood. So I think that's the key point. In the project itself, we also combine our expertise with that of Cobalt Water. So Cobalt Water has specific N2O expertise, and really their models lend themselves quite nicely to our existing treatment system optimization approach. So we combine our existing optimization capabilities on the energy and chemical front with the N2O expertise from Cobalt Water, and together through different AI or machine learning models, we build a single multi-objective optimization capability. And I'll touch on how that works in a couple of slides. So firstly, really what we do is we collect real-time data from the site and build or feed that into our models, which provides an initial set of recommendations that are mostly focused on dissolved oxygen when it comes to nitrous oxide and energy optimization. But ingesting that real-time data serves to initially identify which optimization strategy we're currently in. So depending on the availability and the quality of the data at that moment in time, we've got a main optimization strategy aiming to optimize within multiple different objectives. We've got a fallback strategy in case there is some lacking data, or there's the existing strategy, which is basically a return to business as usual for the operators. So we take a lot of that real-time data. We also feed it to Cobalt, who then provide adjustments to the DO recommendations based on the anticipated N2O emissions. We then take those recommendations and feed them back into our own treatment system optimization engine to check for mainly effluent compliance limits. And then we combine that into a final recommendations for dissolved oxygen per lane and per zone for each of the ASPs. Click on. So here there's an example that we've pulled out based on Cobalt's expertise, where really based on the N2O data that has been available from the Strongford site, we made an assessment of risk in each of the ASPs. And here I think one of the key points that is to be made is that we can see that there's a higher risk on ASP 3 than for ASP 5 and 6, for example. So that in itself provides great insights back to the operators to review really how ASP 3 is operated against ASP 5 or 6 and identify potential tweaks to the operating strategy to lower that risk. Another example that we pulled out is from ASP 3 lane 1 zone 1. But yeah, I think this is really to take a closer look at the N2O emissions picture. So indeed, one of the key points we've noticed is that the recommended level of dissolved oxygen is consistently below what we've recommended. So on the graph, I think first the thing to point out is at the bottom of a graph you see a purple and green line. So the purple is the measured N2O, and the green is the predicted N2O in milligrams per liter. And I think you can see that there's a very good level of fit between what has been measured and what has been predicted using our machine learning models. In addition to that, you can see that there's periods where there's risk generated to a low DO set point. So those is the blue line going up and down a lot. But there's also periods of risk generated by high DO. So that's the red line. But really, I think the key point is that we consistently see that there's a high period, well, there's a long period of risk generated by having too low DO, and occasionally periods where there's risk generated by having the too high DO set point. So really what we aim to do is by fine-tuning the recommendations for DO set points, we can remove a lot of the risk for each of the ASPs. So how does this work in practice? So we have an optimization engine which relies basically on real-time inputs. So the multi-objective optimization that we after is a net reduction of greenhouse gases emissions, and we will do so by controlling the DO set points. But always you want to make sure that what you're recommending is compliant with the standards. So we implement some hard optimization constraints, and there's an additional safety margin which is adjustable based on the risk appetite. Typically, we have a high risk appetite at first in our implementation, and this, as confidence in the system is gained, we reduce the safety margin according to the desired level of risk appetite. And then once the final effluent compliant limits are met, then we really pivot into a net reduction of greenhouse gas emissions. In our case, we focused on the ASPs and optimizing for emissions reductions, but also energy use. But balancing those two out basically means that using CO2 equivalents, we will almost always maximize the reduction of N2O emissions and then optimize or trying to leave energy expenditures to a minimum. So we will, we expect to almost always aim for a maximal reduction of N2O emissions, unless the energy pictures changes fundamentally. So I think that brings it to the end of my part. So yeah, happy to take questions on that in the chat, and I'll hand over to Jeevan.
Hello. Thank you, Timon, and thanks for everyone on the call. Happy to take you through the sort of model integration and the live demonstration of the digital twin application. So without further ado, let me just take control of the screen. So I just want to talk you through a little bit of context about how we've put this whole solution together. You know, as has been touched on in the previous sections, a lot of it has to do with integrating to the data on site. And for this, we've built sort of a variety of data pipelines that get consolidated into the cloud platform. Following this, we go through a process of training and configuring models, as well as interfacing to the solutions provided by Siemens and Xylem. And this provides you with your model layer. And playing live data through this is where you get your visualization capability that James Ballard spoke about at the start of the presentation. If we were to swap the inputs from live data to user-generated inputs that a user can put through the system, this enables the simulation capability of the digital twin, allowing users to test what-if scenarios. And ultimately, there's an optimization layer in the background that iterates through multiple and various permutations of process inputs. And from this, we can derive the optimal way to run the site and provide this back to the user via a set of optimization set points. I'll now quickly just touch on architecturally what the solution looks like before I do the live demonstration. Basically, we've leveraged the Microsoft Azure cloud platform and consolidated a host of databases and data pipelines in order to bring the requisite data needed for the models into the system. From there, we do a combination of virtual machines as well as Databricks to orchestrate the models. So we interface with the Siemens and Xylem solutions via virtual machines and a host of the other models, the AI-based models inside of Databricks. All of these work together in sort of a computational graph, and based on the live data or based on the simulation data that's played through the system, we write a set of results to the database. And then this is all consolidated and collated and relayed to a back-end and front-end virtual machine that provides an API for the data, as well as provide a front-end interface that users can interact with. And what I'll do next is just quickly share my screen and take you through a demo of the user experience of the digital twin, to kind of bring it to life. So without further ado, let me quickly share my screen. All right. So I just want to check, is everybody able to see a screen? It says Severn Trent on the top left-hand side. All good? Perfect. All right. So without further ado, I'll talk about the digital twin in terms of the three capabilities. When you land in the application, the first thing you're greeted by is the visualization element of the digital twin. And for this, we visualized the Strongford Treatment Works as a 3D geospatial view with the assets visualized and tagged by its treatment stages. We also present the high-level site performance KPIs in this sort of bottom bar. And what we do above and beyond that is provide the context around the data. So we reflect energy usage information as well as emissions information broken down into its constituent gases and show the context around that. So you can get to see a breakdown of where each of the emissions come from, as well as a time series profile associated with that. We also, as you've probably picked up from the view right now, that the assets are color-coded into red, amber, green based on their criticality state. Underperforming assets are colored red. Those in sort of an alert state are colored orange, and those that are performing well or optimally are colored green. So this allows users to, at a glance, see where there's issues on site. And if they wanted to, they could zoom into that particular treatment process and see the analytics that are pertinent to that. So we reflect that in terms of emissions, flow, and power. And we also reflect that in terms of golden measures, which is a Severn Trent way of reflecting performance measures at the site. Now, you've now sort of seen the high-level view at the treatment stage level, but we also provide the view of the most granular elements of the system, you get to see what we call the schematic view. And what this shows is the interconnection of individual treatment assets underneath that stage, as well as all of the various flows that comprise that, not various flows, various monitors that comprise that stage. And as James mentioned earlier, visualization is one element of the digital twin, but there's another that is about the predictive analytics. And for that, we provide forecasts of where the models are available, the measures and monitors of a treatment stage, so that you can get a view 24 hours in advance of performance. And what this enables users to do is see problems before they happen and resolve them before they happen. So that is the sort of capability one that talks about visualization and a little bit of predictive analytics. What I'll do next is talk about simulations, which a user can configure via something we call the simulation wizard. So a user enters this and can basically create a simulation by giving it a name, and following this, configure various elements of the simulation. So what we allow users to do is at the highest level, configure flow to the works. So they could do this in two ways. They could play a radar rainfall forecast through the system, so they can anticipate what effects weather will have on the system. We also allow users to play arbitrary rainfall patterns, so they could simulate heavy rainfall on their catchment and how the treatment works would be able to deal with it. Users are also able to test taking assets in and out of service so that it can more effectively represent the way the site is configured at the moment. So if something is out of service for maintenance, they can basically reflect it in this, or if they wanted to simulate a maintenance scenario, they could do it via this interface as well. We also allow users to configure in a great level of granular detail individual performance parameters. So they could do, for example, sensitivity analyses on a range of DO parameters, as well as other parameters on site. So the way the sludge stream works, the way the digesters are working, the way the liquor treatment plant is working, all these are configurable via the parameter configuration page. Once everything is set up, a user simply clicks Run Simulation, and then they get presented with a backlog of simulations that have been run historically, and theirs is just queued on the background, on the back end for running. Once the simulation has been completed and run, a user can just see the status of it and also view the result. So what this presents you with is the simulated results for all of the relevant KPIs on the site. It shows us both as what is the baseline performance, so what is the current performance on the site, and what the simulation would, or what the site would do on the highest level if the simulation was run. And we show this on the highest level as well as on the most granular level, so that a user can look at this and determine whether their plan changes to site will be effective. And they can use this as a way of doing a data rationalized way of operating the site. So this is the simulation capability. And at this point, you could probably see that you as a user can come to a better than baseline way of operating the site. However, to achieve that true mathematical optimum, you need to run hundreds, maybe thousands of simulations. And that's not tractable from a human perspective. So for this, we implement an AI optimization routine in the background that intelligently searches the parameter space of the site, and it pulls out the parameters that will drive down emissions performance while keeping effluent compliance in check and energy performance in check. And we surface this to the user as optimization recommendations. And basically, this is the series of set points that a user can influence. And we present that basically as a set of what the current set points are and what the optimized set points should be, so that the user can plug this into the system by themselves and then drive the optimization of the site. We also show what the performance of the site will be without any optimization applied. So this is the baseline predicted output. And we also show what the optimized predicted output would be, so that users can get a clear idea of what the trade-offs would be if they were to implement the optimization recommendations. And I think that is the demo nicely completed. And then I'll pass back to Leah so she can just reshare the slides. Yeah, thank you.
Thank you, Jeevan. James, I think that's the right one, right?
I think so. Brilliant.
Perfect.
Right, so we've got just one slide to finish us off here before the break, I believe, and that is benefits. So you've heard a lot of the great work, you've heard about our journey. You're now asking, yeah, okay, so what have we seen then, and what are the benefits? Well, I'm just going to talk for a couple of minutes because I'm aware probably the most benefit out of here will come out from the discussions. But I'm going to take a couple of minutes to talk about there's benefits of the project. And there's benefits of the digital twin. And I actually just want to start with the project before I dive into some of the stuff on that slide. If I think about, there's three kind of core benefits I've seen from this project: internal engagement, value of collaboration, and learning about challenges to scaling. So just picking those up. Internal engagement. I speak at quite a few conferences and events over the last 5 years. There's been major talking points, if not one of the most critical talking points for digital events is around adoption and challenges to adoption for digital tools, be it AI, digital twins. The more kind of operator level of staff are worried that AI and digital twins are going to take their jobs and it's going to replace them. And the more senior staff are generally more worried about AI opening the door to Skynet type technology and Terminator stuff. But actually, one of the real benefits of doing a collaborative project, especially the innovation style project, we've really dug deep in our engagement as part of this project. So we've got into the operational teams and really worked this through with them. And we've also been working at a senior level. So we've gone right across the board. And that's why I've got a quote on the top of that slide there. We'll run the works on this, no doubt. It will be our main tool. So 3 years ago, would I have thought an operator would give us a quote like that for a digital tool that can help optimize waste? Absolutely not. Actually, today, as we start to get into the nitty gritty and build this stuff out, we are hearing this type of comment from our operations teams. And I just thought that one was so powerful because they did actually say it. So yeah, so internal engagement, really key. It's going to be a massive lesson learned for sure, but real benefit. Collaboration itself, so internal collaboration, I kind of touched upon. External collaboration, the fact that we have a collaborative project, we've got partners that have all these different experiences from different countries, different sectors, and actually bringing all of that into what we're trying to do here is absolutely critical and absolutely key. We can't go at it alone as a water sector. We need to learn from others. So really going through and learning the value of collaborating with all of these different partners has been really good. And challenges to scaling. So we do have lessons learned after the break, but I'm just going to reinforce the fact that doing these types of projects means that you can start to understand the challenges. We get comments even today about things like digital twins. When we know we've got to scale them, we know the challenge is, let's get them everywhere. Let's not just have one instance. We need it everywhere. We need it end to end, just copy and paste. It's not until you actually start to work through this stuff that you start to realize why copy and paste isn't quite as easy as just saying those couple of words. So you'll hear more after the break on why, but I just wanted to reinforce that actually by going through these type of projects, you start to understand and can actually articulate why, which is really important when we start to think about what future collaborative projects do we need in order to enable this type of stuff for the sector. Okay, now we move on to benefits of the actual digital twin. So this is where you'd love to see a load of dashboards with numbers and 20% here and 30% there. Truth is, we're still working through this stuff. We have run simulations that have given us indicative values. Hesitant to give you any major figures. I can say from the graphs that you can see in front of you, if you sat down and worked it out on the bottom one, it would look at about a 5% reduction. So this obviously needs to be validated. The next stage of this project is to work through the simulations that we've got, how to actually go through and validate them, and then move to implement these control strategies in the real world. The one on the top, the nice blue dotted line going across, turning into yellow and green, that one though is really worth focusing on. That is our inflow model, flow and load. So that is really understanding what goes into the works. I think one of the biggest benefits of this project for me is understanding how important what comes into your, the input of your digital tool, what comes in. Because without that, what are you optimizing really? How effective is your digital twin going to be? So nailing that, and we've done that through data science and analytics, is absolutely key. So really understanding the environmental impacts, how to expand that back into the network as we start to look end to end, source, tap, drain to river. What's coming in? Where is the weather hitting us? Where are customers turning on taps? How does that flow through to the treatment works? Is absolutely key. And I think they're the critical learnings. So I think that's probably time for a break.
Thanks, James. And thank you to all the presenters so far. It's been a really great informative session so far. So we are just going to go to a quick break. We're running slightly over time, so it's just going to be a super short one. Let everyone go to the toilets, grab some drinks. So we're just going to do a 5-minute break. You don't need to go anywhere. You don't need to leave the call. Your cameras and mics are already off. So feel free to just leave your desks and come back in 5 minutes time. Just before the break, just on the screen here, you can see a QR code. That's just for our next upcoming spring knowledge sharing event. So anybody who's enjoyed today and has an interest in water efficiency, which is the next theme of the next webinar, please do feel free to scan that QR code to find more information. My colleague will also be putting the poll in the chat over the break, so please do, if you have to drop off at all after the break, just make sure to fill that in before you go. As we say, it really helps us shape the value of these webinars moving forwards. So that being said, the time is now 11:10. We'll have a 5-minute break, so we'll be returning at exactly 11:15. Thanks, everyone. Okay, so the time is now 11:15. So I'm going to give everyone a moment to come back. And after the break, we'll be going into a bit of a deeper dive into the key lessons learned. So if the presenters, I think it is James and Di, if you could come on, get your cameras and mics on, ready for that, that'd be great. Cool. Well, it's 11:15, so we shall restart the session. James, do you want to kick it off, or Di?
Yeah, I think Di's going to start us off.
Perfect.
Hi everyone, can you hear me okay?
Yeah.
Great, thank you. So for the lessons learned, basically we'll just go through people, process, technology and data. I will just go through the first two elements, people and process. I believe James will then kind of chat on about the technology and data. So I think before the break, James has already mentioned quite a lot of literally just the key lessons learned is how we're going to engage in on the people, and that will basically just build on that one, maybe just give it a little bit more detail, or maybe at a micro level. And there was a two element that I would like to touch on. The first one is actually the collaboration. So if we think about digital twin, how it works, generally we need sensor, collect data, feed the data, then take the data out of the sensor, collect into the storage, take it to the cloud, build a model, etc. So generally, we need to work on with the sensor supply, especially currently we have a lot of new challenges, new parameters that we need to measure. Then we need to engage with the new sensor suppliers. We need to talk to the servicing contractor, or maybe we need them to properly maintain the sensor, and then we need internal ICA support to help us to get the data, and also through the tag pass into the cloud, and then our partner will be able to receive it on the other side of the cloud, and then make sure that the data is actually in the right format. And then with the process knowledge support giving to the modeling expert, then we build the model, etc. So this is definitely not a one-man job or one team job, and definitely require a lot of collaboration internally with all the department, and also externally with all our partner. And especially as you can see in this digital twin, we'll have data model, mechanics model. There is a lot of data we start passing over. So this is one of the key things we need to really good collaboration. And to enable that, I think the important thing will definitely use the engagement. And I think James has already touched on internally, we did really good stakeholder engagement. And here I would like to also give credit to our partner, because I think we also did quite a good job in doing the user engagement, because like in innovation, gaining the end user support is really, really crucial for embedding any successful innovation. And in this case, digital twin, it's actually a tool that like we hope that all will use like every day. And then we need to make sure that they feel confident and also they're willing to use it. So the approach that we're taking is we basically go through everything, the whole process with them. So at the beginning, for example, once we identify the user, and then we just did in-depth like interview with them to capture the user story and requirement, when we started to shape the digital twin, and then we definitely need to let them know that like what sort of thing that you ask for will be able to deliver, what sort of thing that we won't become, because like the model can't do everything. And during the delivery, we regularly provide them with update, and then also to collect feedback. And the purpose is like we need to make sure that everyone is actually on the same page. And we need to ensure the requirements are met, no matter on the model function and then the user interface. And I think some of the question in the chat is about like how they were going to try that. And so once we have like the model function being online, it will be like bit by bit, and then we'll just put up a session with them, like really long session with them to allow them to try and then the feedback and etc. to make sure that they know what we are doing and in that space. So the second part it is generally the process. So if you think about like digital twin model, and then we are capturing quite a lot of things, for example, like how we are going to, when we try to build a model, how we're going to choose like suitable model, how we do those like assess criteria, how to make the decision. And then when we once build a model, and then we need to understand like what the methodology will be, what sort of data that we will need. And I think most important on the modeling side is about the calibration, also validation. So I think maybe a little bit different from a physical project. The model actually, once it's online, is not going to finish. Is actually the start of the process, because we need to constantly like calibrate it, validate it. And this is something that I'm just actively working on. So we are trying to set up some of the methodology and also some key criteria to let us like to first of all is understand how accurate the model is. And then also when we started to see something might not go wrong, and then how we are going to like improve and validate it. And it is supposed to be a regular activity. And apart from the modeling, the digital twin is actually an operational tool. And so we need to put in process to enable the operator or the process scientist to know like how they will be able to use the model to inform their like day-to-day operational control. But if we take one step back from that one, just like what I previously said, like sensor data acquisition, model and car, the very beginning is actually we just need to have like the sensor to collect the correct data. And this is I've seen in the chat, a lot of people asking that one, and this is really, really crucial. And this is one of the really, really key lessons learned that we found in here. So at the moment, we're actively working with the site and also the sensor supplier, and also the servicing contractor to understand how generally the spec of the sensor, like what their needs will be, how often we need to like calibrate them, and also generally what the sensor like and they don't like. And also like once we collect the data, we also need to make sure the data that we collect is okay, and then we are pulling up a lot of like different work on it to how to review those data to make sure that we're okay to take out some of the outlier, but not taking out a lot of things, because sometimes it's not because of the sensor is not working well, it is because the process the control is not working, not as we expected, but the sensor is working okay. So this is a lot of like really brain heavy work, and I think all our partners and also internally in Severn Trent we're actively working on it. And I believe when we finish the wrap of the project, we'll have something really meaningful we'll be able to roll out in Severn Trent and share to the sector. So I'm going to pass it over to James.
Yeah, thanks, Di. I think I'll jump onto the data points you're making and expand from there. So adoption of these tools is absolutely going to be fundamentally based on how good your data is. And we really need to know that to scale this stuff, you can get the data from as close to the source as possible, and that it's going to be available, high quality and usable. So kind of through this project, we've been building a data framework that can help us to address that. So we know that we need the data to be at the right time. We know that we need it to feed the models. We know we need it to be calibrated. And then we need to get it back. And this is where you kind of get that IT-OT convergence go on. So when we look at the work that we've done, you start by, we've got a site with a site SCADA system, and you think we've got 1,000 treatment works, and the vast majority don't have a site SCADA system as such, or a standalone server network SCADA system. So each of the sites will have varying different levels of technologies. Some might hoover the data up into an outstation and send it to an enterprise level. Some process it locally on a site SCADA. Others don't, mainly just revolve around a PLC in a very small space with a HMI. You're going to have a big mix. So one thing we're going to have to work through is how do we build a scalable data acquisition system, solution, design, architecture that can actually take the data that we need, because we've learned that the more you process that data, it starts to get filtered, it starts to get lost, it starts to get grouped in different ways and different formats. And actually, by the time you get the data to your models, if you're not careful, you end up getting the wrong data, patchy data, gaps in data, or it can't actually align with your enterprise systems. So you still need to be able to know, if I have a pump, that pump's registered in your asset management systems, it might be SAP, we use SAP. That pump needs to be associated with the data that's going on site, which needs to be associated with the models. So one of the critical learnings I'd say with data is, and something we need to really strongly work on over the next few years, is to scale this stuff. How do we get that data and link it through to all of the different systems? What else have we got? We've got alerts and alarms. So one of the things that I hasn't touched upon that I think is really key is the alerts and alarms. So we think about this tool, it's going to generate insights. How on earth are we going to take that insights and actually drive the benefit and get that benefit realization? And one of the real benefits of this project for us has been the engagement of our internal transformation teams, starting to look at how do we centrally manage these tools and systems? How do we then triage that data through, run these models, but yeah, triage the outputs into useful alerts, proactive alerts, and then set our processes up such that the right people can react at the right time. So that's something else that we're working through. And I think a big lessons learned is you can't stop at the tool, you can't stop at the model. You really have to have all of the processes and people in place to be able to use those outputs. And the final point that I think I'll make on data and technology is around cyber. So really going forward, I think there was a question, there will be many questions going forward around bidirectional control, real-time control, optimizational control, whatever you want to call it. Ultimately, the aim is to influence set points in our controllers and our control loops. As soon as you start to do that, even if you do it through human in the loop, so the model's recommended a set point, a human needs to look at that and validate it. Actually, yeah, do you know what? I think that is a good idea. I'm going to take that recommendation and I'm going to put it in the controller. Now, you might drive out the site and do it. You might press a button. As soon as you take that recommendation and implement it in the real life, you have closed the control loop. You are part of the control system. So cyber security, and specifically zero trust architecture, is going to be really key going forwards. And that's something I expect to see a lot of drive and development on through AMP8, through all the water companies, making sure that as we get smarter and your tools get smarter, and the insights get smarter, we're remembering to go with that cyber zero trust. So it's not just cyber as in hacking, it's also functional safety as in can you look back and see all the different recommendations, when they were made, who they were made to, how did you process those recommendations? All of this needs to be true in order to have a secure system, and that will help build trust, I think, in the outputs and the tool itself. So data availability, quality, usability, SCADA systems and data acquisition, we talked about that. We talked about cybersecurity and functional safety, and we talked about alerts and alarms. So I think that wraps up my bit.
Are you done, James? I thought you had one more slides on the conclusion and wrap up, but that's fine.
Oh, sorry, I actually forgot to take control. So
you're absolutely fine.
Well, look, another slide. Just as I planned it, I have one more slide. to wrap up. So yeah, so I guess data ability, usability and quality is up there because I just can't emphasize that enough. I think all the discussions that you have around digital twins, whether you're building it for waste treatment works, water treatment works, networks, or whether they're digital twins of the catchment and external activities, the way you get your data, the way you process it, making it available at the right time to the right people in the right format, and not losing that data quality through the journey, getting processed in one SCADA system or a cloud engine. You then get a filtered, less granular view into your system. Really mapping that out with data models is absolutely key. So you can't skip that part and go, well, we're just going to get flow data, we're just going to get weather data. Really digging in, taking the time to dig into those data models is going to be worth it. Digital twin is like a kitchen. So I think about the ingredients. Oops, I'm taking a control. Right, I think about the ingredients as data. So you can make sure you have the highest quality ingredients and highest quality data, but you need to think about how you're going to cook your lovely roast dinner. You know, some people might throw everything in the microwave and get okay mixed results, and you might just about enjoy it. Other people might steam some things and oven some things and microwave other things. And it's that combination of, and what we need to work at as a sector is, how are we all going about it? Are we all going about it in the same way, cooking using the same devices, or in some instances, is it better to shove everything in the microwave essentially? So that's something we're learning and we're working through. And integration guardrails. So the final learning that we've got from this, I think my ultimate conclusion is the importance of scalable, maintainable, manageable digital twins, which need to be following guardrails. So guardrails tell you the realms you can operate within safely. It tells you the type of things you need to consider when it comes to standards, legislation, and it tells you ultimately how you're going to deliver the tool. So these need to span across from alerts, alarms, data, technology, people, processes. We need to have these documents in place so that as we build each of our digital twins, they all align to the same setup, the same standards, and can be ultimately linked together and are robust. So yeah, if we don't have those guardrails, and ultimately linking sector-wide, industry-wide guardrails, I think will be really key. But for now, in this project, we're learning from what we've done and creating our first set of internal guardrails. Now I think I am done.
I was warily turning my video and camera back on. Cool. Okay. Thank you, James. And thank you to all the presenters that have joined us today. It's been a really great session. If everyone wants to, all the presenters could pop their cameras and mics back on, please, for the Q&A. We will go into the Q&A now. So I'm just going to stop sharing my screen quickly so that everybody can have a better view of our lovely presenters. Great, we've had some great questions in so far, but if anything does occur to you while we're doing this Q&A, please feel free to keep submitting your questions in the chat, and we'll try and get around to them as best we can. So first question, I think, is actually for Jeevan from Ale, who wants to know what if data is delayed, missed, or corrupted? How does the digital twin deal with that? And does it estimate the missing values, ignore them, or switch to a backup model?
Thanks for that question. So there's two parts to this, right? So the first one is the way it currently operates. So Adam may have mentioned it, Timon may have mentioned, but we have these soft-sensed estimated values that come out of the models, and that essentially pads for where the data is poor or missing. And this leads me to the second part of it, which is sort of the future state of the digital twin and how we factor in user feedback, right? So if we were to see something that looks erroneous or where there's data missing, a user, and this has been requested from some of the user sessions, that they would like to counterfactually label that data as poor so that it can be factored into the relearning process and we effectively taken out if it is poor or missing data from the system. So I hope that answers the question.
Great, thank you, Jeevan. Next question from Chris. I think Jess and James, this is probably one for you guys. And Chris has asked, it would be interesting to hear about the practicalities of relying on the instrument data streams and the level of additional effort, if any, required to maintain that required quality level across the many data streams for the plant. Does it take more maintenance or calibration, or more sophisticated filtering for erroneous data? More discipline from operations staff about manual interventions, etc. That was quite a large one, so if you wanted me to repeat any of that, just let me know.
I'll start off with the operator bit and I'll hand over to James on the instrumentation side. So yes, we know existing assets on site can be a bit of a nightmare depending on the age of the asset, the level of investment over the last AMP or previous AMPs, and it's actually something we've been facing into as part of the Net Zero Hub, not just on the digital twin. So how do you put new sophisticated technologies, whether it's digital or physical, biological, into aging assets? And one of the things we've had to do is actually do a detailed review of all of the sensor footprint on Strongford. So Jeremy and I have been working through that, so understanding kind of what is the quality of the data there. And actually at Strongford it's been quite nice because we have a very engaged site manager, Andy Marsh, who's very engaged in the digital twin. He's been very proactive, so getting them on board from the early stages of this project has been the key output of that. But that's just Strongford. We're going to be doing 33 more of these, so there's going to be a lot more engagement that we've done. So we are, although we're still in the validating part of the models, the model's been built, but we need to go into validation, and that's our activities over the next couple of months. We've taken a no regrets activity to engage with every level of the business. So whether it goes from our senior stakeholders, our business lead, our strat leads, all the way down to operators. And we've brought in a business change, and we're going to have business change partners to help us understand what are the new OPEX numbers, the base numbers that need to be able to maintain the sensors, what is the new sensor footprint, what does that look like for the budget. But a lot of the kind of arguments to bring them in line with doing this is around the benefits to them and showing them how this helps with their OPEX actually, because one of the things that we talked about earlier is we're looking at final compliance and process emissions as the two important things, but we're also looking at how we can improve their OPEX from electricity usage and chemical usage, which is really important because they are driven by budgets. As soon as the budget goes up, your sensor calibration is one of the first things to potentially leave. So it's that trade-off. So we're working through that messaging. So we've got some really, as anything, you know, promoters and detractors. So there's a lot of ongoing kind of engagement work within my team to get that. From a sensor perspective, I'll hand over to James as the instrumentation architect.
Well, I'm just thinking back to, you know, we've got thousands of sites that they're very old, you know, and a lot of them can be incredibly small sites. So typically, historically, you put in sensors that are directly needed for the control system on the site to do exactly what it's meant to do and nothing more. Nowadays, with models insights, we are looking to gain additional data through Strongford. We've learned, you know, the types of additional data that we need that are directly relevant to the models. So you know, the gap analysis that Jess mentioned is going to be absolutely critical. Getting a list of here is the critical points that we need this model to work, and getting that reviewed against sites. There's going to be a lot of gaps because, you know, a lot of this data is going to be used for the models and not for direct necessary control on site. But you've got a direct line through to the benefits now. Whereas, you know, not so many years ago, the general view of sensors is we just need more data. We need more data. We need more sensors. And you do get a lot of pushback at that point because it's another sensor to maintain. It's another sensor and it costs money. The data costs money. Everything costs money. And if you can't get that direct line through to the benefit, it's going to be very difficult. So there will be more sensors required, but there will be incredibly targeted sensors, no doubt, driven through a gap analysis, and then the maintenance and calibration will be aligned to those benefits they'll be receiving from using the tool.
Great, thank you, James. Perfect. Okay, so going back to Jeevan, who has another question, and they just wanted to ask, how are the ML models in your digital twin trained and updated? Are they retrained regularly with new operational data, or do they rely on static historical data sets?
Yeah, thanks again for the question. So related to that, within the Databricks environment, we maintain a ML flow log of all the model metrics. So we, you know, just for example's sake, log the mean absolute errors, RMSE, as well as mean absolute percentage errors. And we use these models tracked day on day to evaluate the performance of each. We use the metrics to evaluate the performance of each model. And where there is a deviation detected in model performance, we trigger a retraining based on the latest available data that we have. And in this way, we try to keep the models up to date within the system.
Perfect. Thank you. Timon, coming to you, a question from Naren, who wants to know, you mentioned the model is not black box. What kind of model is being used and what kind of architecture is being used?
Yeah, thank you for the question. Well, I suppose, I mean, the architecture is a traditional architecture, so we do work with artificial neural networks, but also other machine learning techniques. But I think my point was much more about trying to bring, well, in this case, the Severn Trent operators and subject matter experts along in the process. So as we build the models, be as transparent as we can in terms of what we're putting into the training data set, what we're leaving out, how we're cleansing and filtering the data. And that is an iterative process where we do need to go back to the operators or the people that are aware of or can have an educated eye on the data and inform us whether or not some of the trends or anomalies we see in the data are representative, should be kept in or should be filtered out. But there's also other techniques that we use, like performing different sensitivity analysis, or as we retrain the models and feed it with additional data, we monitor the quality of the outputs, and then we iterate on that to understand, okay, any changes that we see, what could that be down to? So it's really a back and forth as we build the models to, yeah, as best as we can be transparent and open up that black box to understand what the data model is doing.
Great, thank you so much. This next question from Lisa, I think a few people will have some answers for it, so I'll throw it out as an open one to the group. But Lisa says, thank you for the presentation so far. How long have you / will you baseline the site emissions to fine tune the twin? How much adjustment do you think will need to be made to the twin as you move to other sites, accounting for site specific processes, configurations, etc.?
If I give a start, I'll probably have Jeevan and Di and Jeremy come in for it in a minute.
Absolutely.
So one of the things we did when we talked about the contexting for the net zero hub generally is put a lot of process emissions monitoring before we even started the net zero hub. So we have about 3 years of process emissions data at Strongford on an annual basis, and we have that wider across all of a few of our sites. We're probably about 9 sites in at the moment, but we do have plans to roll out process emissions monitoring ahead of deploying any more digital twins in year 1 of AMP8, so we can start understanding that data as a start of the 10. But one of the things we have definitely learned is every site gives a complete different from a process emissions perspective, and it's one of the things that I'm working in my wider role. And what we've taken the approach, and I know Jane will be able to explain this a bit better after, is that we're trying to take a cookie cutter approach as possible into the actual model or the model configurations. What is really different is going to be the kind of surrounding inputs and outputs. So actually the site is configured differently with a different anoxic zone, a different HRT, different flow and load splits. But what we're actually actively doing now is we've taken all these lessons learned from what kind of data that we need, and we started to develop what we're calling site survey technical assessments, and that's broken up into ET, OT and IT. And we're going to be starting for our rollout. What are all the data points? What are the flow and load bits? Getting the process scientists on board who know these sites at the back of their hand to give us all of that input data to try and make as life as smooth as possible. But I'll hand over to Jeevan just to give more around kind of how that cookie cutter approach that we've taken.
Great.
Yep. So in terms of that cookie cutter approach, I think it largely falls down to the way the models are going to be configured, right? So we've got sort of standard approaches from a mechanistic perspective, as well as a machine learning perspective of how to build the models. What we then do is essentially analyze the nuances of each site so that we can configure the models appropriately to that site. And in that way, based on how Strongford is being validated and calibrated, have more confidence in the way the models will output emissions profiles for that. And once more data comes online with respect to emissions performance, we can obviously calibrate and update the models at the various sites. Thank you. Anyone else, I guess, from the team can add on to that?
Jeremy, did you have any thoughts that you'd like to add to that question at all?
Just a small comment, really, in terms of rolling out. Once again, it does mean understanding what each individual process is, but generally they are, as Jess has said, it's that cookie cutter. You've got things that can be replicated from Strongford into other processes, but understanding how each process works, they're always slightly different and they have to be knitted together.
Great, thank you so much. Jessica, coming back to you from Lisa again, who just wanted to expand on the question. The use of what-of scenarios is really helpful to operations when planning changes. Within the project at Strongford, how much are existing operators being engaged with the twin, and what feedback have you had from them to date? Do you think they'll need any additional training or experience to be able to utilise the approach for operational interventions?
Yeah, so we mentioned earlier we've had a lot of engagement with the site operations team, but actually it's probably one of our lessons learned. We probably went a good 6 months into the project with not doing the level of engagement that we really wanted to do with the right people, and we looked inwardly at ourselves and went, have we got all the right requirements? Have we got all the right people spoken to? And actually sometimes you might not have always got it right at the beginning, so we did actually go, let's do a bit of a pause, let's make sure we've got everyone really understood. We've had those engagements with the operations team, so there was lots and lots of sessions run by Santec in terms of requirements for the operators, and not everyone is going to get everything. So as soon as you start to do these, people want it to be somewhere where they hold all of their standard operating procedures, then becomes their overall alarming tool, and you're not going to get everything. We then had to do a bit of a Moscow analysis on what we actually could do based on the original scope of the project around the capabilities, and we fed all of this back into the operations teams, and they've had lots of sessions direct with the Strongford team, and we split into wastewater recycling and bioresources, so lots of requirement sessions were done with them. They were followed up in terms of, you said this is what you've been produced, and you saw a quote earlier that says that was from the site manager Andy Marsh, that said this is a tool that we will definitely use. So that's the overarching feedback that we've had. In the last 2 months, Kate and my team couldn't make the call to Nation Holiday. Has spent a lot of time with Juven and the rest of the Santec team doing a lot of direct engagement sessions. We've been polling all of the feedback associated to that, and generally it's been very positive. A lot of people, I think, would have a lot of, we talked about digital twins maybe 2 years ago when we started this. It wasn't really a reality, and we're now coming back and going, this is a reality, and it shows you and it gives people confidence of what it is. Going into the question around upskilling, completely, there's going to be a massive level of upskilling in being able to use this. So there are going to probably be different types of user interfaces who need this. So you might have, the team manager and the senior technician on site who needs to go into that and drill down into every single asset, and maybe need more upskilling from the process scientist team. And because this is single at the moment, it's not really changing the ways of working on site. With 33 more of these, we really are looking at what does the transformation look like. And what we're already doing is now engaging with our academy team. So we have a separate academy team that trains our operations team. And there's a new work stream being created for digital twins, and what does digital twins look like, and upskilling. So does it have to be a process engineer, for example, that runs all of the sites, for example, in that? Is it a new level of technician that's needed who does a lot of the simulations themselves? And the other thing we're thinking about is actually you've got contradiction business units. So you've got a bioresources business unit and a wastewater recycling unit that might have different goals that day. How do you make the decisions in that day of what's the priority? Is it reducing chemical usage? Is it final compliance? Is it biogeneration? And you're going to have those tensions. So we're in the very beginning stages of this to work out what does the transformation look like. You've got the question of actually a site is run locally. Do you go to centralised? Do you not? So all of those kind of conversations are now being had because of the fact that we're going to be funded to do 33 more of these, and it's a fundamental change to the way we're going to be operating over the next AMP.
Great, thank you. Sounds like there is a lot to think about with this, which is interesting. Thank you so much, Jessica. Next question for Jeevan again, who They are asking if someone tries to send fake data into the system, can the digital twin detect it and then ignore it or confuse it, sort of thing?
Thank you for the question. So on that one, right, I think I'm trying to answer it from two perspectives. So one element of how we've collaborated on the digital twin is to work with Severn Trent Tech on strict cybersecurity principles and guardrails, right? So we presented an initial architecture upon which the digital twin will be based, and subsequently worked with tech to essentially encase the solution in strict cybersecurity guardrails. So in this way, there's virtually no opportunity to inject fake data, because it's the data is so locked down that it's an impossibility to inject this false information. The second part is going back to my first bit of information, which is we have these models that estimate the state, and we can detect where the state deviates from what is coming in from the data significantly, and use that as a means of, in this sort of very impossible scenario, flagging when fake data might come in. So that might be one way of doing it, but it's not intrinsically built into the tool at the moment. Thank you.
But if I just jump in there, it's worth saying that going back to the cyber and zero trust focus that we've got over the next AMP, we'll be building that out. So you've got the bits that we're talking about, which is validation of data as it comes in, which the scalable tool will absolutely have to have. Is the data sensible that I'm seeing? What kind of anomalies is going on? How do we, trigger? What do we need to trigger? Do we need to trigger an intervention? Is it an investigation? Is it just a flat out, it's a spike, it's an erroneous data? But you then need to go one step further, which is what happens if somebody takes an output of the tool driven through erroneous data, whether it's injected or fake, or whether actually it's just a genuine error in the sensor data causing, and there's plenty of reasons why you could have erroneous data from the sensors, from external factors. Maybe a plant's blown under one of the sensors. So you get this output. Can somebody actually go and change a set point on the site outside of sensible limits? So you do have to start to make sure that your actual control systems on site, which ultimately have the control logic, it has the backup systems, it has the failure modes, your control logic on site is king. That stuff needs to understand and have sensible limits and bands, so that even if you took something that was potentially not sensible and tried to change it, it wouldn't work. It'd still have to be within sensible bands, and it would still have to be logged and tracked and follow all of those international standards, IEC 61511, etc. So we'll be working that through when for the scalable product.
Cool, thank you, James. Great addition. So coming back to you, James, and Jess, I think too, and maybe even Jeevan, given the independence of process components and the numerous variables involved, is it practical for operators to manually implement feedback control actions suggested by optimization tools and AI model predictions, such as changes in aeration, RAS rate, or MLSS concentration? Are there automated control loops available to handle such adjustments? And additionally, how does the GPROMS model contribute to this process?
So quite a big question there. So I think we separate it up into a few bits. So just as a starter for 10 on the operators, I completely agree that there's going to be a lot of offset points that have to be updated. That's kind of no different to what they have to do today at the moment. They just do it all very manually. So what actually happens at the moment is they've got a set of calculations on an Excel. The process scientist runs a couple of calculations, gives the set points for the operators, and the operators then go and do that. So you're not actually changing the fundamental processes, you're making this easier for them to do. So in terms of them doing that, there may be more, and there's likely to go be more, because they might just set it for once for the day and go, that's it for the day. But the digital twin may say, actually, you've got a storm coming, it's time to change. So there is going to be that level of increase, but that's as part of the next kind of activities that we're going to be doing over the next couple of months, is validating the model and then seeing how the operators actually interact with it. So our current kind of expectation, it's maybe a 10% plus extra in terms of work, but it's making their current life easier in terms of what they have to do today. And we need to kind of validate what that increase looks like. Ideally, we want to get to an automated control, but I'll let James step in here.
Well, I mean, the thing we've got to remember is that in our application, this isn't kind of millisecond control. This is a process that can take 8 to 12 hours to go through waste treatment. And generally the water sector is relatively slow. It's not microsecond stuff. So what this tool is doing is helping to inform the settings that then prepare the site for the upcoming hours, days. So as Jess said, we have operators that their day job today is to make sure that those set points are sensible. This will just help to inform that. The starting point is absolutely going to be human in the loop. What we need to work through as part of that cybersecure data acquisition is how do we get to a point where you could either press a button, centrally, and it safely updates set points. So we'll start obviously with sites with control rooms and a team looking at it. I think it's going to be quite far in the future. You get to an automatic world, albeit the capability of actually transferring the set point automatically today, very easy, very straightforward. Getting it working as a system, incredibly complex. Let's start with human in the loop, get our cyber right, get our safety right, get the benefits realized, and then build out from there.
Just one comment for me as well, as there's a GPROMS element mentioned there. I think one thing that's important is to remember the different users that involve in different ways around the system. So for those who are not process engineers, getting into the detail of a process flow diagram and maybe understanding a P&ID, and all they might be like, what is all this? The important thing is they're not exposed to that in the work that they do, and instead they may see the front end that Jeevan showed, or it may be they just actually get the list of the recommended set points from that. And so I think within the overall package, we've been taking a lot of consideration to think about who are the primary user group that will be engaging with this part of the system, and how do we ensure this is something that meets their needs and their limits. So please, don't be put off by the apparent complexity of anything you might have seen under the hood. There are people who are excited to engage with that, and we'll let them have fun with it.
Great, thank you, Adam. Jeevan, did you have anything you wanted to add to that question at all, or? I
was just going to say that I think there's different flavors of optimization that take place in the background. I could speak for the Sandtech part, as we use a sort of Bayesian gradient search approach, and I think each of the partners as well have a different way of running the optimizations. And we keep this sort of in the background and just surface the results so that it's an easy to use application. Thank you.
Perfect, thank you. We are coming to the end of the meeting. I think we have time for just a couple more questions. I just want to say thank you to the audience for all of your great questions. We've had a lot through, and thank you to the presenters as well for such detailed, great, informative answers. I just wanted to say, if you haven't had your question answered yet today to the audience, don't worry. I will be sending around all of the unanswered questions to the presenters after this call. So the answers to your questions should end up in the case study as well, alongside the recording on our platform. So with that said, I'll bring us to the last couple of questions before we close the meeting. So Adam, coming back to you, somebody just wanted to ask, how do the GPROMS model and the optimization model and the AI model differ in terms of the type of data they process and the insights they generate? How are these data and outputs interconnected across the models? Oh, you're just on mute, Adam, sorry.
There we go. Good question. I think one of the first observations is that actually everybody works off a common set of data. So there's no siloing or separation of that data, and I think that's really important. The second thing is that while, as Jeevan said, there are multiple different types of optimization that can work, one of the important architectural design principles was to ensure that the AI models and the mechanistic models can speak to each other. So the outputs from an AI model can feed as an input into a mechanistic model, and so on. So if you imagine that process flow diagram, you actually do have a process. There are some loops in it, but you have your process working through it. The idea is all those different things interconnect. And choices were made then about deciding for each unit operation, is this something that should be a AI model or a mechanistic model? And maybe if there's further interest, we can go into the decision making around that. When does it make sense to use mechanistic or AI? But I think the headline point there, as to say, is number one, it's the same common set of data for each. Number two, everything's all linked in together. And thirdly, it's then viewed from an optimization perspective. either based on an individual stage or in a site-wide optimization itself. So, and I think that's really important as well, is to be able to allow users to be able to optimize or run scenarios around a particular area or across the whole site if they wish to.
Great, thank you, Adam. I'll just wrap up by coming to Di, who had a question from Michael, who wanted to ask, I assume you measured the N2O in a liquid phase. You mentioned that at DO levels lower than recommended, the measured N2O increased. However, could this also be a result of the reduced airflow required for a lower DO, resulting in less N2O emissions, and due to this, an increased N2O measured in the liquid phase?
I think yes, because if we break down, we do our N2O measurement in the liquid phase, and this is the common approach. And if we generally break down that equation to calculate the emission this long into this long, and generally it could be considered just like dissolved N2O concentration times the airflow. So if we adjust the airflow, and then high airflow could result in lower N2O, and sometimes lower N2O and could result back into higher the N2O. So it's always a balance that we need to make, and that's the reason why we definitely need a model to support. And especially there is some also some other element is like in some cases, yeah, let's say concentration potential lower the emission produced in there, but using doing like higher direction also like comes with a higher energy consumption. For example, electricity, if that is also generated from the fossil fuel, and then we definitely need a model to look holistically to understand what is the total emission, not just focus on what is producing from the biological process, but the related ones as well.
Great, thank you, Di. We just have 1 minute left. I don't know if anybody wants to add any final thoughts to that answer, but if not, I will wrap up the showcase now. Perfect, great. So that brings us to the end of today's showcase. Thank you so much again to the audience for taking time out of your day to join us today. We really hope that you found it valuable. And we will just be sharing the poll again now, because I can see that not everybody has responded just yet. It should only take a couple of minutes, and I can't emphasise enough how valuable your inputs are for Spring, as well as the project team that have presented today. So please do take a moment to leave feedback before you leave the call today. Thank you also again to the presenters for all of the hard work leading up today. And for sharing the learning so openly and honestly from this project. We really appreciate it. And with that being said, I will let everybody get going. As I say, the recording from today's event will be alongside the case study on our Spring platform after this event. So if you follow us on LinkedIn, you'll see when that is available to view. Thanks again, everyone, and I hope you enjoy the rest of your day. Thanks.
Thanks.